In this video, I will be talking to you about the different properties and categorizations of waves. A wave is a disturbance that carries energy from one place to another. Matter is not carried with the wave. A wave can move through matter, called a medium, but some waves do not need a medium to be able to move. If a wave needs a medium, we call it a mechanical wave. If a wave can travel without a medium, for example through space, we call it an electromagnetic wave. We have to look into the properties of their categorizations. One way waves are categorized is through the orientation of particle motion relative to the direction of energy propagation. The three notable categories of waves are longitudinal, transverse, and surface. Longitudinal waves occur when the movement of the particles in a medium are parallel to the motion of energy. A good example of longitudinal waves would be a slinky effect. Notice how it creates a push and pull motion.
Waves don't always move like this. Now, sometimes they move like this. They squeeze together and spread apart. That's how waves go through something like the spring. Watch. I'll squeeze this end and let go. See, there's a wave going through the spring just by squeezing and spreading. There's no motion up and down. It's the same way sound waves travel through the air. Air molecules bump into each other, so some places they're close together, and other places they're spread far apart. The air molecules are moving kind of like these pool balls.
He's got it!
There, it worked. That's because the billiard balls were close together. Now the molecules in air, well, they're very close together, so sound travels great.
Transverse waves occur when the movement of the particles in a medium are parallel to the motion of energy. Light and radio waves of all frequencies are transverse. Anything from microwaves to infrared to ultraviolet and gamma rays are also transverse. To better visualize the transverse wave, try vibrating a guitar string.
Light, the vibrations of a plucked string, and water waves are all good examples. Let's look at a water wave. The wave travels from left to right, and the vibrations are up and down. The vibrations are said to be moving in a transverse direction to the direction of motion. If we look edge on at the wave, we can see that the up and down vibrations are symmetrical about a center line. The maximum distance the vibration moves away from the wave center line is called the amplitude of the wave. The amplitude essentially tells us how noticeable the wave is. Imagine that I stand in a fixed position and count how many peaks pass me in a given time. I might, for example, count 20 peaks in 10 seconds. I can then ask, if 20 pass me in 10 seconds, how many would pass me in 1 second? The answer is 20 divided by 10. So 2. I can say the frequency of peaks passing me is 2 per second. This is the frequency of the wave. It doesn't matter whether you count peaks, troughs, or somewhere in between, as long as you count the same part of the wave every time.
Surface waves occur when the movement of the particles end up having a circular motion. You can observe surface waves in the ocean. To better visualize the surface wave, however, try dropping a floating object on the water. You will notice that it will make a circular motion on the vertical plane. Another way to categorize waves is on the basis of the wave's ability or inability to transmit energy through a vacuum. This brings up two categories: electromagnetic waves and mechanical waves. Electromagnetic waves are the waves that can transmit energy through a vacuum, which means that no particles have to be in the medium. Light is an example of an electromagnetic wave. How do we know? Light from the sun passes through the vacuum of space before it gets to the atmosphere of the Earth. Anything from microwaves to infrared to ultraviolet and gamma rays are also electromagnetic.
So the electromagnetic spectrum is made up of these electromagnetic waves, and they go from high energy, really high frequency, low wavelength gamma rays all the way down to long wavelength, low energy radio waves. Remember, you're only seeing a small portion of that. But the one thing these all have in common is that they're made up of electromagnetic waves. Those are transverse waves. Remember, what a transverse wave is one where the oscillations are perpendicular or at 90 degrees to the direction of the movement of the wave. And so it's not only in one dimension, we also have electric fields and magnetic fields that are perpendicular to themselves. And so we have oscillations that are both perpendicular to the direction of motion and the corresponding field. And so they can travel through anything. Electromagnetic waves can travel through medium, like light can move through water, obviously, or radio waves can move through the walls of my house so I can hear the radio, but they can also move through the vacuum of space. And so if we look at electromagnetic waves, remember, as we move towards high energy gamma rays, our wavelength is decreasing, but our frequency is increasing. So radio waves have really long wavelengths around the size of a building, whereas gamma rays would be more the size of an atom itself. But if we look at how they oscillate, remember the wave is going to move in this direction and the oscillation is going to be perpendicular to that. But adding on top of that, we also have these fields. And so the direction of the wave is going to be, we'll say, from left to right in this dimension. But we're also going to have in the Z dimension, we're going to have these electric fields that oscillate back and forth. And then in the Y, or rather in the X, we're going to have magnetic fields that go back and forth. And so to give you a visual of what they really look like, we have these oscillations in these two dimensions, and then the movement is going to be in the third dimension.
On the other end, we have mechanical waves. These waves can only transmit energy through particles, which means they do not work in vacuums. A sound wave is an example of a mechanical wave. Sound is essentially the effect of vibrations being moved through air particles. In space, there is no sound because there is no air. Except for light, almost all the waves we experience are mechanical.